Medical Institute and 2014 Nobel laureate in chemistry. Eric received his bachelor's degree in physics from Caltech and his PhD in applied physics and engineering from Cornell University. He followed that up with a very interesting path in science. So he, while he was trained as an experimental physicist, he moved on to become a member of the Semiconductor Physics Research Department at AT&T Bell Labs. He worked for a number of years after that as a scientific consultant before he joined Janelia in 2005, where he's been a group leader ever since. So I know from good authority that Eric's not a big fan of prizes, but he's won quite a few, so if I can mention some of them. So he shared the 2014 Nobel Prize in Chemistry for the development of super-resolved fluorescent microscopy. He's a recipient of the William L. McMillan Award and the National Academy of Sciences Award for innovations for initiatives in research. He's a member of the National Academy of Sciences and an honorary fellow of the Royal Society of Chemistry. And he was just recently selected for the 2015 Newcomb Cleveland Prize of the American Association for the Advancement of Science. Today he's going to be talking on the physics and engineering of advanced microscopes for biological discovery. Without further ado, please join me in welcoming Dr. Eric Betzig to UC Berkeley.
Thanks a lot, Steve, and thank you all for coming today. So I won the Nobel Prize for, as Steve said, something called super-resolved fluorescence microscopy. So what the heck does that mean? Well, if that's the size of a protein molecule, then if you look at it in a regular optical microscope, that fuzzy blob is what you would see. So in other words, the standard microscope is 2 orders of magnitude too coarse to see single molecules. Now, of course, this is to a great extent a problem because one of the central mysteries for me in biology is how do single molecules, which are inanimate little specks, somehow come together and self-assemble to make this bag called the cell that can move and can reproduce and can excrete and eat. And the way we're going to be able to understand that is through structural biology, but it has to be combined with dynamic imaging as well. And that's where optics really plays a key role. And so I was motivated by this problem going all the way back to grad school in '82 when I went to Cornell and worked on what was known as the Nearfield optical microscope. So the goal of my advisors, Mike Isaacson and Aaron Lewis, was to make an optical microscope that could allow us to study living cells at the resolution of an electron microscope. And the concept was if we had a glass fiber probe that we coated with metal except at the end, and the end of that probe was therefore had a, say, 1/10 of a wavelength diameter aperture in it, then when we shine light down the probe, we would initially illuminate just a 50 nanometer or so region of the sample. We could then scan that little nano flashlight point by point and get an image. And so I worked on that technology first for my thesis and then for 6 years as a PI at Bell Labs after that. Got to the point where one time we had the world record for data storage density, looked at histology sections, and actually did the first super resolution fluorescence imaging, in this case of fixed cells, and looking at the actin cytoskeleton all the way back in '93. But the 2 experiments that became more important for my eventual career were in the latter stages of my time at Bell. The first was when we were looking at that actin cytoskeleton, it was pretty clear from our signal to noise that we should have the sensitivity to see single fluorescent molecules. And at that time, that was a very hot topic because just a few years earlier, my co-laureate, W.E. Morner, had shown near absolute zero the spectral signature of single molecules. And so many people wanted to extend that at room temperature. The problem isn't so much the amount of signal that you get from a single molecule, but there's all sorts of background that washes out that signal in a diffraction limited spot. But with near field, you greatly restrict the area you illuminate, so it becomes very easy to do single molecule imaging. In fact, this was probably one of the most important papers of my time there, one of the most cited, and it was a 1 afternoon experiment, so for the whole paper. So what we found is that instead of looking like just round blobs, the molecules had these weird shapes, like you can see this little double guy here and like that. And it turned out that when we thought about it, what was happening was a fluorescent molecule is acting as an electric dipole. What was happening was that dipole was actually acting as the probe to sense the electric field components inside of the near field aperture. So in a sense, we were doing kind of molecular resolution mapping of the fields of the small probe. And furthermore, by then comparing that to a model that Hans Bethe had developed for subwavelength diffraction back in the 40s, we were able to determine exactly what these shapes should be for any given orientation, and therefore back out the orientations. Furthermore, once we knew the shapes, we could fit to those shapes, and then even in the presence of fairly low signal to noise, determine the positions of these molecules down to about a 50th of the wavelength of light in all 3 dimensions. So the other experiment that turned out to be very important was when I teamed up with my best friend at Bell, Harold Hess, who was doing low temperature scanning tunneling microscopy. And so we wanted to do low temperature, high spectral resolution, high spatial resolution imaging of quantum well structures, these aluminum gallium arsenide heterostructures that give rise to like the emission in this laser pointer. And so when we pulled out his STM tip and put in my near field tip, what we found is that the squishy spectra that you see with diffraction limited imaging broke up into a bunch of atomically sharp lines. And furthermore, these lines would be entirely different if we moved 100 nanometers away. And what we eventually realized what was going on is that the light emission inside of these quantum wells could not be produced anywhere it wanted to, but once excitons were created by absorbing the light, the excitons would diffuse around and then get trapped into little potholes due to atomic variations in the roughness of the interfaces due to the MBE. And once they were trapped there, then they would eventually collapse, emit their photons, and emit the photons in a color based on the thickness of the quantum well at that location. And so even though there might be a dozen or more exciton recombination sites underneath the near field aperture, we could still resolve them in some sense because our spectral resolution was good enough that they all were in separate colors. And so if we looked at them in a higher dimensional space of x, y, lambda, then you could interrogate each one individually and study it. And that was the focus of that paper. So at this time, I'd been doing near field for a dozen years. And what I discovered in those days, and what I've discovered time and time again since, is that science is very faddish. And particularly technology and applied physics is extremely faddish. And it goes through a curve like this. This is where I like to get in, where I think I perceive an opportunity that other people either don't believe in or haven't figured or haven't thought about yet. This is the time to dive in. And eventually nobody believes in it. And you work and you work and you iterate and you try to do better. And eventually you start to realize you're on the right track. And then things start to get really exciting. And that's the sweet spot. That's when it's really fun to be in the field. But eventually everybody starts to see what's going on and they say, hey, I want a piece of the action too. A lot of people get into the fields. And what I find is what happens is because of the way people have to get funding or whatever, basically the signal in the field stays the same, but the noise goes to infinity as everybody starts to claim the impossible and the ridiculous. And so that's exactly what happened with Nearfield, is the quality of the work went into the tank while the amount of good work stayed the same. And it frustrated the hell out of me. And so I had an expectation of this for the trajectory of it. This is what people were claiming, and the reality, as I'll explain in a minute, ended up being like that. Okay, so having developed many new tools over the course of my career, every new one, because of your investment in it, is like a newborn baby. And you hope that it's going to cure cancer, become president. In the end, you're happy if it stays out of jail. Okay, so Nearfield barely stayed out of jail, but still, it still frustrated the hell out of me to see people overselling it. In the end, I really got to the point where I felt like every good paper we published was doing nothing more than providing the justification for 100 bad papers to follow in its wake. And it was a waste of time and a waste of the taxpayers' money. And everything I had done was a net negative to society. So that's me. Okay. So, but the other reason for my frustration was not just the hype, but the Achilles heel of Nearfield. And that's that, you can do this on the back of an envelope from the wave equation. You can see exactly how darn short the evanescent fields are and how quickly they fall off with distance. And even if you take your aperture 25 nanometers away from the sample, you get a very significant loss of resolution. But remember, my dream was to be able to see living cells with the resolution of an electron microscope, and a cell is a hell of a lot rougher than 25 nanometers. So Nearfield was definitely not the path to get there. And then the final thing was just at Bell, how hard it was to succeed and how hard we worked. So I latched on to Harold as my best friend right from the beginning. And he and I always prided ourselves on being the hardest working people in a hard working place. So we would get in at 4:30 in the morning, and if he beat me, I would put my hand on the hood of the car to find out by temperature how many minutes he had beat me by. And then we would go in and we would work, and we'd work until 6, go to the same Chinese restaurant every night, go back into the lab, work till 10, then come back 4:30 the next morning, and repeat that 7 days a week. And that's the life we lived, and after 5 years, it made us look like that. So for me, when you put in all of the frustrations I had with Nearfield with just simple exhaustion, I was done, and I quit, and I didn't have any idea what I wanted to do next. But I found it, actually, one of the other things I found over time is that for me, creativity arises from a combination of a long period of intense concentration on a subject with no interruption, followed by getting away from it for a brief period of time. And literally within just a couple months of being unemployed and trying to flush Nearfield out of my head, while I was pushing my daughter around in a stroller, it popped into my head that you could combine the last 2 experiments I described to make a different way to beat the diffraction limit. So the idea is, if you want to look at fluorescence, you're looking at discrete molecules, and those molecules are distributed in a sample so close packed together that their fuzzy blobs overlap. You can't do a lot with that. But if, as in the quantum well experiment, these things glowed in different colors, or they turned on at different times, or they had different polarizations, or some discriminating feature, you can isolate them in a higher dimensional space. Once they're isolated, then you can fit the expected point spread function to the measured shape and determine the center of the distribution in much better precision than the width of the distribution, and therefore find the coordinates of the molecules and project that to the XY coordinates. You find all those coordinates, you got a molecular resolution map of the sample. So that was the idea. So I published that, but I knew right away that there was a catch. And that's, in a normal biological sample, there might be thousands of molecules in one diffraction limited spot. So you need exquisite resolution in that third dimension to see one on top of all of the others. And short of running back to Harold and say, hey, let's try this at 2 degrees Kelvin, which was going to be a hero experiment, I really didn't want to get involved in it. But I'm glad I published the paper. I almost didn't. It's only been cited about 100 times. But one of those 100 was the Nobel Committee, because that was one of the 2 papers they used to justify giving me the prize. So in the end, I always knew I had a backup option, and that was to work for my father's machine tool company in Michigan. So they end up making these very large customized machines that's the size of this auditorium or bigger, that would be designed specifically to make, an intake manifold or a brake caliper or so forth for the auto industry. And so I learned the ropes there, and after about 7 years, I created this beast, which basically tried to take all of the function of one of those large machines and collapse it into something the size of a compact car. And the trick was to use a discarded technology based on hydraulic motion control, because hydraulic motors have a power to weight ratio that's way higher than electric drives. And you can think of a multi-axis machining center very much like a Saturn V rocket, in that much of the weight of the rocket comes from pushing the fuel of the upper stages by the lower stage. And so just like in that, when the hydraulic motors get much smaller, then you're pushing much less weight on successive stages. The whole machine collapses in size because the Young's moduluses of the materials are fixed, the stiffness goes up, and then you can take more aggressive cuts. And so it was a really big win. It used hybrid energy storage principles like you have in hybrid cars, And so it would move 4 tons at 8 g's of acceleration, position that load anywhere within inside a meter cube volume in 100 milliseconds to 5 micron precision. I spent 4 years developing it, 3 years selling it, and in the end I ended up selling 2 of them. And so that wasn't enough to be a success, as you may have gathered. So in the end I decided to fall on my sword and said, I did everything I could, Dad. I'm sorry to blow a couple $1 million of your money, but it's time for me to do something else. I had no idea what that something else would be. I sort of felt like maybe it's time to look back at science. I knew it would be a problem because I hadn't done science in 10 years. But the thing that finally got me back was when I read Chalfie's paper on green fluorescent protein. So the idea that you could snip a bit of DNA out of a glowing jellyfish and splice that into the DNA of any organism you want and get that organism in the living form to express that protein with that glowing tag on it, to me was magic. Because when I was trying to do biology with Nearfield, the microscope was a big pain in the neck. But an even bigger pain in the neck was bringing in dyes to be able to specifically label the features we want to see and not have a lot of background or poor labeling density, etc. And GFP was clearly the answer to this. And so I decided I need to do microscopes again. The problem is I don't have any intellectual capital because it's been 10 years since I've written a paper. So I needed an idea. So I holed up in our cottage for a couple years, and eventually I found inspiration in optical lattices, which are interference patterns. A simple optical lattice in 1D, of course, is just the standing wave, where 2 wave vectors come together. But in higher dimensions, and with either 3 or 4, you get 2 or 3D optical lattices. This has been used in the AMO field to trap atoms and cool them. It's also been used to make photonic crystals and things of that sort. And I thought, well, maybe I could use an optical lattice to create a massively parallel 3D excitation field for high-speed volumetric imaging to apply that to green fluorescent protein. And what I found is I developed this theory that found new classes of optical lattices that actually decoupled the period of the lattice from the wavelength of light, which the previous lattices had that bound to them. And that allowed me to separate these lattice points far enough that they'd be independently optically addressable, and so I could have that microscope the way I wanted. I figured out ways of exciting that through microscope objectives, and that's what I went on the road to try to sell. And so one of the places, well, the very first place I went was to my buddy Harold, who had left to work for a test equipment company working on disk drives in San Diego after Bell imploded, and I was trying to get him to go on this idea with me. He was interested, but not that interested, because he said it was my idea and it would be chewing my cud if he was working on that, and he wanted his own cud to chew. But he was willing to help me find a place, and one of the places we went was Florida State University, where we met this guy, Mike Davidson. He told us about a new type of fluorescent protein that had just come on the scene. In a normal fluorescent protein, you shine blue light on it and it glows green. With these guys, called photoactivated fluorescent proteins, you shine the blue light on it and nothing happens. But if you shine violet light first, you photoconvert that protein to an active state, and then blue light will make it glow. So this is in the unconverted state, this is in the converted state. And so Harold and I were sitting in the airport in Tallahassee, and we realized this was the missing link to make that idea I had pitched and abandoned 10 years earlier to work. Because if we could just turn on the violet light very low, then stochastically only a couple molecules would come on at a time, and they would likely be separated by more than diffraction limit, and then we could find the centers of their fuzzy balls, and then turn those off, turn on another subset stochastically, and eventually build our super resolution image. So it was the idea I had 10 years before, except in time, instead of in wavelength as we did with those exciton recombination centers. And so we realized that, you know, we were both very excited about this idea and terrified, because we said, why hasn't anybody done this already? This is so bloody simple. So we were very scared, and we said, we got to do it right away. And so it was going to take too long to get VC funding or too long to get a grant. And so we said, well, we just better do this ourselves. So, so when I left Bell, I told them to go to hell. When Harold left Bell, he was able to take all of his equipment with him. So we pulled a lot of that out of the storage shed, and then we put $25K each of our own money in it. And normally you would do it in the garage, but we could do it in his living room because he wasn't married, and it was a lot more comfortable. And so, so we also needed expertise in biology because you're talking to two condensed matter physicists who knew nothing about biology at that time. And I was scheduled to go on at a talk at NIH to try to sell my Lattice microscope. And I begged them if I could speak to George Patterson and Jennifer Lippincott-Schwartz, who were the inventors of PAGFP, while I was there. I took them to lunch, swore them to secrecy, told them our idea, and Jennifer said, fantastic. And I didn't realize at that time, Jennifer says fantastic to everybody and everything, but we took that as a yes. And so when we had the microscope ready, we shipped it there. And within a month, with George's help, we were taking cryosections through cells. These are some lysosomes, these sort of garbage dumps of protein degradation in the cell. Here we're turning on the violet light so you can see the single molecules coming on. If you sum all of the fuzzy blobs, you get the diffraction limited image. But if you find the centers, you start building up something with more information. And after 20,000 frames, you go from that to that. And to better appreciate, if you zoom in, you go from that to that. So with dense enough labeling, and that's the Achilles heel of super resolution, you can get to 20 nanometer resolution in your living room. So this, of course, became, immediately a big deal, and it's so easy to do. It's easy to do the technology. It's not easy to do the labeling. But in any case, lots of people jumped into it right away, and then we were off to the races. So in that same lucky year of 2005, within the same month when we came up with the Palm idea, I got hooked up with something I had never heard of before called the Howard Hughes Medical Institute. And within a couple months, I was on their payroll, and Harold and I went from rags to riches because HHMI is one of the most generous outfits you can imagine. And we started living and breathing Palm for a few years. The initial experiments that got us that science paper and got me the Nobel Prize, we went from the idea to all of the data in that paper that led to that prize in 6 months. And that's what you can do when you're two guys who are scared enough and motivated enough working in a living room together. So the bad news is that Harold has just missed out on 3 Nobel Prizes. He was the guy who came up with the evaporative cooling concept that was centered at Bose-Einstein condensation. He found the core states at the center of the Abrikosov flux lattice that Abrikosov got the Nobel Prize for, and he should have been involved in the Nobel Prize here. But Harold, being the humble guy he is happy that he doesn't have a Nobel Prize and has to deal with things like this that I have to do. But anyway, he still gets to have fun. Anyway, so over those next couple years, we worked on a number of things. One was with Jan Lippert while he was here at Berkeley, looking at chemotaxis receptors in E. coli. And Jan collaborated with Ned Wingreen at Princeton, who was able to develop a model to show that our experimental data in terms of the sizes of these clusters and their positions along the bacterium are completely predictable in terms of stochastic self-assembly, where the proteins are randomly inserted in the membrane and then move around and then stick to an existing cluster with a probability equal to the size of that cluster. Same way that you get a stretched exponential distribution of water droplets in clouds. We were able to show that proteins such as these in focal adhesions that contact to the extracellular matrix around the cell that look co-localized at the diffraction limit actually aren't. With Bob Pigeon's group at Janelia, we were able to show that certain core promoters necessary for gene expression are segregated away from the nuclear membrane, and there's some genes that hug up against the nuclear membrane. And this spatial segregation is one of the ways the cell uses to regulate gene expression. And with Tom Blanpede's group at University of Maryland, we were able to show that the actin, which is necessary to give the shape to the dendritic spines on the postsynaptic side of these neurons, is only polymerized in certain discrete locations that give rise to that shape. So that's all the good news, and now the bad news about super resolution. So the biggest Achilles heel is nothing more than the Nyquist sampling theorem. So if I have a sine wave like this, if I sample this often, I can see that sine wave well. If I sample every half period, I could lose that sine wave altogether. Now imagine those samples as nothing more than the fluorescent localized molecules, and you'll understand that at small enough features, it's absolutely essential to be able to decorate them with lots of molecules. If you do the back of the envelope calculation for 20 nanometer resolution in 2D, you need to be able to have up to 500 molecules in a diffraction limited spot. Now the trouble is that biologists have never had to have fluorescent densities like this before. Sometimes you get it naturally, but oftentimes you don't. And so this becomes really limiting. The other problem is of course, that means you need to be able to see one fluorescent molecule on top of 499 others. The good news, and the way we got lucky, is that the photoactivated fluorescent proteins we worked with right away were ones that had contrast ratios of thousands to 1, so we were safe. But there's been many, many probes people have used for localization microscopy since that have very poor contrast ratios. And as a result, people get poor data. And as a result, I lived the same bad nightmare all over again with super resolution that I did with Nearfield back in the day. And so by 2008, I was as sick of Nearfield as sick of Palm as I had been of Nearfield back in the mid-90s. And the reality is even worse than that, because what you're doing is you're getting a stochastic sampling of an underlying molecular distribution. And that stochasticity comes from two causes. First, how well you label the sample, and that's a stochastic process, and then how you activate it and read it out, which is another stochastic process. So you have two levels of noise on top of the actual target proteins, which are really the thing you care about. And so really you have to go up to almost an order of magnitude past Nyquist to really have the sort of signal and the noise necessary to be unambiguous about seeing the feature you want. That's insane labeling densities. It's doable, but extremely hard. So, and then you can also ask yourself, well, what's the big deal about super resolution fluorescence? Because after all, you know, I mean, we've had electron microscopes, tunneling microscopes, X-ray microscopes. They have pretty damn good resolution. Well, there's two advantages of fluorescence. The first is as a structural biology tool, it offers specificity to specific proteins that the other tools don't. And so that's one major advantage. The other, of course, is that it's pretty much the only game in town for doing live imaging, or optics is. You know, or you can do a little bit of AFM and like that, but if you really want interesting contrast for biologists, fluorescence in live cell is really the game in town. So let's think about that. So if we're going to do structural imaging, 95% of what we've learned from super resolution is on chemically fixed cells. But the goal of chemical fixatives is to cross-link proteins. So you get immediate changes to the ultrastructure just from preparing the sample. So here you can see we blow out a lot of the actin filaments. Here we're looking at the endoplasmic reticulum, a protein sorting machinery in the cell. When we look at it live, it looks fairly continuous, but when you fix it, all those proteins aggregate and it looks like something completely different. And so, you know, I go to a lot of conferences where the theme is seeing is believing, and I always tell them, how can we believe what we see? You know, there's so many steps from any image is a very imperfect representation of reality, which is the sample. There's sample preparation artifacts, there's imaging artifacts, and so forth. And you have to take damn care about those things in order to interpret your results. And so now let's take the other fork in the road other than fixed. That would be doing it live. So if we do it live, the problem is that the two methods that share the Nobel Prize, STED and localization, require cell and intensities that are orders of magnitude higher than people ever had to do with the diffraction limit, and the excitation intensities are anywhere up to 10 to the 10th as high as the 10th of a watt per square centimeter that life evolved under. And there's been precious few controls about what the hell this is doing to the cell. You know, so these methods are really not very compatible with live cell imaging. We've done some with localization, but it's a pretty limited tool. So this should be obvious, because if you want higher spatial resolution, you need more pixels. If you need more pixels, you need to take more measurements. That's going to take more time, and it means you're throwing more potentially damaging light at the specimen while you're taking those measurements. So if you're going to be honest, there's always these trade-offs between spatial resolution, phototoxicity, speed, and how deep your image is. So there's the good news is that there's a third method of super resolution fluorescence, which did not share the Nobel Prize, which isn't as bad in these regards, and that's called structured illumination microscopy. In this technique, you don't illuminate the sample uniformly, but use a standing wave to create a grading of excitation across the sample. That grading pattern then beats against the spatial frequencies of information in the sample to demodulate spatial frequencies up to twice beyond the diffraction limit within the diffraction limited passband of the microscope. And by taking a number of images with different phases and orientations of that pattern, you can do a Fourier space reconstruction of the image that extends the resolution out by a factor of 2 in each dimension, or 4 versus 8 in 3D in terms of total gain of resolution, and hence the amount of photons required. Well, that's 4 to 8, that's doable. I mean, you can get that. So what I'm saying is that the reason the Nobel Committee decided to not give SIM part of the Nobel Prize was because it is still diffraction limited in a sense, because it only gets a 2x gain beyond the diffraction limit, where the other methods are theoretically diffraction unlimited. But really that weakness of SIM is its strength, because first, you don't need such insane labeling densities, and second, it requires a hell of a lot less light, orders of magnitude less light than the other methods, and it's far faster because you need so many fewer measurements to be able to reconstruct a super resolution image in SIM. And so the guy who understands these trade-offs faster than any of us was Mats Gustafsson, who developed SIM while he was a postdoc at UCSF. And then we recruited him to Geneva in 2008. But in 2009, he was diagnosed with a glioblastoma, and he died in 2011. So when he died, I ended up inheriting much of his group, and I was bound and determined to try to convince the world of how great SIM is and see if there were ways that we could contribute to improve upon it. So you can see some of the benefits of SIM here, is that whereas any other super resolution technique doing live imaging would be lucky to get a dozen images, here you're looking at the endoplasmic reticulum now for 1,800 time points. So at least 2 orders of magnitude higher than anything else. Now, yeah, it's only 100 nanometer resolution, but look at the wealth of information you have by being able to look at sub-second rates at the ER. And what you learn is that the cell is a pretty goddamn crazy dynamic place. It's beautiful and it's scary with the complexity. That's one protein out of 10,000 that's doing that kind of dance in the same sort of, tens of microns of volume on a side package. It's a problem that should fascinate physicists like crazy. And this field totally needs more physicists to understand how the hell the cell works. It's a problem in complexity and emergent properties and everything else. With the SIM, we have tools that can really get a lot of dynamics out of this. This is doing SIM imaging now at 50 frames a second. So we can really now get to the point where we can see with super resolution the rates at which things are actually happening in the cell. So if the knock against SIM, and the reason why I didn't share in the Nobel Prize, is because of that limited resolution, one of the foci of my group has been, how do we get around that limitation? Well, the simple and stupid thing is to try to increase the diffraction limit of your lens. And so Olympus sells an objective that runs in total internal reflection that's up to 1.7 NA. Well, with that, when you double that resolution, that means you get down to about 84 nanometer resolution now in the GFP channel, which is pretty darn good. And the other advantage of SIM compared to STED and Palm is that you don't need specialized switchable labels. They're labels that can take a ticking, so you can use standard fluorophores, and it's easy to do multicolor imaging. Here you're looking at focal adhesions again, like I showed earlier, in 2 colors, but now you're seeing it live for at least 100 time points. Here you're watching the actin-myosin contractions, that contractile machinery that generates the forces to make the cell move on the sample. So that's great for 80 nanometers, but what if we want to shoot even higher? So this is something Mats was working on when he died with his graduate student Hesper. And the idea is that you have to now start using these switching ideas, but apply them to SIM. So what they did is they take a photoswitchable fluorescent molecule, activate all of those molecules as you would instead a resolve, and then use a standing wave to turn off all the molecules except the ones near the nodes. The residual pools have high harmonics associated with them that allow you to demodulate even higher spatial frequencies in the sample to within the passband and extend the resolution further. In Hesper's case, to about 50 nanometers with actin, but it required 900 seconds to get a single image, so not exactly live cell compatible. So what my postdoc and I, Dong, realized when we thought about this is that this principle of saturated depletion, where you turn on all of the molecules and then turn off all except at a node, is really not an optimal way to do live cell imaging, because it takes time and energy to switch the molecules from one state to another, and then more time and energy to turn them back off again. And most of those molecules that you turn up and down immediately are not contributing any photons to your image. It's only the residual pool that is. So it's very photon inefficient, and it's very high dose and very slow, and that's the problem with that approach. So what we realized would be a better approach is to use a standing wave to activate only a subset of molecules, and then a second standing wave to read out those molecules. So that gets us 2 harmonics. So it's still in some way diffraction limited. It's just now diffraction limited to 3 times beyond the diffraction limit, which takes us down to 62 nanometer resolution. And then we can then, as if you've seen this movie flash back and forth, be able to then really be able to follow at very high resolution at second or sub-second acquisitions for around 40 frames, in this case, the actin cytoskeleton. This is really the state of the art of live super resolution imaging. There's really nothing else that can get that quality of image at that speed for that many frames. And the reason for that is, in our paper that we published on this, is we wanted to do sort of a grand unified theory of all super resolution methods and their photon efficiencies. And in order to understand that, one of the other pet peeves I have about the microscopy community that has developed is the whole notion of resolution and trying to define resolution by a number. A microscope is a spatial filter. And so is there any filter that you describe by just a number? You want to understand the whole filtering properties across the spectrum of that filter. And so a microscope takes squishy, large features and transmits those things effectively. And then as the features get smaller and smaller, it attenuates them until eventually there's a size feature where you get nothing. That's what's known as the diffraction limit. But in practical microscopes, you even rarely reach that point, because to get to that point, you need infinite signal to noise. And so certainly in live imaging, where every photon is precious, you're far from an infinite signal noise environment. So it's really, SNR totally dictates what practical resolution you can get. The SNR dictates it and how fast that function falls off. So that function and how it falls off is called the optical transfer function. And essentially you want a microscope that maintains as high an OTF for as long as you can in frequency space as you go to higher and higher spatial frequencies. It turns out that SIM for resolution above 100 nanometers and nonlinear SIM for resolution below 100 nanometers is by far the most effective. And if you start to analyze then the photon requirements, you'll find that you're on the order of 1 to 2 orders of magnitude less photons for those methods versus STED or PALM or the other methods. And furthermore, if you go through the dose required to activate or deplete or excite the molecules, it's an even bigger difference. So you need orders and orders of magnitude less light. You need orders of magnitude less photons to be able to do these methods versus any of the other super resolution methods. And that's why they're more live cell compatible. So just to show that that theory makes sense with experiment, here we're comparing caveolae, which are a protein that's involved in invaginating and bringing cargoes into the cell. First with the nonlinear SIM. This is a paper done by Stefan Hell's group where they're using this resolve technique similar to STED to look at caveolae. And this is one point from this movie. And you can see that the caveolae should look like rings as they invaginate, because in turf you're just seeing the very top surface. But while the claimed resolution of the result is 54 nanometers or better than this, it's basically at about the diffraction limit. And it just completely infuriates me how low the metrics and standards are for judging resolution in these microscopes. Everybody looks at an isolated feature and draws a line across and calls it their resolution. And that's the most characterization they do. And it's completely incomplete and has no bearing on the situation when you have dense structures together, where the tails of the distribution mean everything in terms of how things overlap and create the signal noise. But even not just the resolution is better, you're talking about a dose that's 1,600 times less and for the activation and 14,000 times less for the others, and an acquisition time that's 0.35 seconds versus 184 seconds to get this versus this. It's not even close, So, and then here's another example now for localization microscopy. This is probably the best localization image I've ever seen of actin. And you can see that this is what we get with PA-NL-SIM. And so you can see the resolution is comparable. Our claimed resolution is 3 times lower, but the speed is such that we're 1,500 times faster. This is a fixed cell. The powers are similar, but not the depletion powers, which are 20 times different. The total dose is 800 times higher. So, if the Nobel Committee thought that SIM didn't deserve to be thought of in the same class as STED and localization because of resolution, I'm here to tell you that it isn't just better in terms of phototoxicity and speed, it is actually better in terms of resolution, often in a practical level. Even if it's still diffraction limited, the practical limitations of those other methods limit them practically, maybe not fundamentally, but practically to levels that aren't as good as we can even get with the nonlinear SIM. So the moral of the story is that while all of us in the super resolution field were crowding up to this apex here to get the one metric we were focused on, spatial resolution, Matz was smarter than us and realized that by backing off in this direction, he'd have a bigger application space all to himself. So in 2008, when I was really frustrated with Palm, I decided that I wanted to take that lesson to heart and see what happens if we go all the way back to the diffraction limit. In other words, is there something that I can do as a physicist to improve the performance of optical microscopes for live cell imaging in terms of other metrics of importance like speed and phototoxicity that would be as much of a gain as the spatial resolution was for Palm? And so the good news is that well, why would you want to do that? Well, structural imaging is fine, but really the thing that defines life is that it's animate, right? So every living thing is a complex thermodynamic pocket of reduced entropy, and matter and energy is flowing through that continuously. So you will get some information from structural imaging, but the only way we're going to answer that fundamental question of how inanimate molecules make the animate cell is by imaging across all 4 dimensions of space-time with high resolution at the same time. Now, the good news is that the standard tools people use to do live cell imaging in 3 dimensions leave a lot of room for improvement. They're basically the wide field microscope and the confocal microscope. The problem with these methods is they run in an epi configuration where they illuminate the entire thickness of the specimen, but there's only a single plane that's in focus at a time. So the other regions either create unnecessary background, and they certainly create unnecessary bleaching and toxicity. So one of the most important innovations in microscopy in the last decade was when Ernst Stelzer at the European Molecular Biology Lab reintroduced a 100-year-old idea called plane illumination. In this type of microscope, you bring a second lens from the side, in this case a cylindrical lens, to create a sheet of light. You position that exactly where the focal plane is, and then there's no bleaching and no toxicity of the regions above and below it at all. There's no background from there. So therefore, you can use a fast wide field camera to snap the information from that plane, then move that plane by plane through the specimen and get your 3D image. This has been transformative for studying embryogenesis at single cell resolution. But it has a problem And that's that diffraction dictates a trade-off between, since it's just a beam waste, how flat the light sheet is over a given field of view and how thick the light sheet is. And if you try to apply that to the dimensions of a single cell, it's about the it has to be about the thickness of the cell, so you don't gain much. So is there something that can be done to change that situation? And there is, and it's a physics trick. And so several times in history, physicists have come up with basically non-diffracting beams, Bessel beams. So I first became aware of these in the late 80s when they were hot. So basically, by restricting all of your illumination to a ring, basically when it comes to a focus through the objective, by illuminating the periphery of the ring, all of the wave vectors have the same kz component to them so that there's no interference between them. And so you get absolutely no variation in the cross-sectional profile of the beam in the z-axis, but you can still vary in the xy plane. If you illuminate with a continuous ring, the function that's created is a very long spear of light, which has the cross-sectional J0 profile, so that's why it's called a Bessel beam. By changing the thickness of the light sheet, you make it a Bessel-Gauss beam, so it's not infinitely long, but then you also reduce the number of side lobes that are inside of here. So we built this Bessel beam microscope where you scan in and out of the plane here while you integrate on a camera, and then you move up, up, up with the beam and the detection objective, get your image through the cell. That sounds slow, but in our modern embodiments, we go 1,000 planes per second through the specimen, or several volumes a second. So like I said, there's a problem, and that's that a Bessel beam isn't just the center spot. It's surrounded by these progressively dimmer side lobes making a bullseye pattern. And when you scan that along, you get some out-of-focus excitation. So we first dealt with that with 2 photon, but a better solution was, instead of scanning the beam continuously, we would step it discretely in the plane. And then we end up writing a grading pattern. And then that grading pattern, because of the side lobes, is actually a 2D kind of lattice pattern. And then we could use Motz's principles of structured illumination to make lemonade out of our lemons and actually poke beyond the diffraction limit in both the scan direction and the vertical direction. That's what you're seeing here. And then here we're able to look, in this case, at a cell that's transfected with a cancer signaling protein that promotes these membrane ruffles that fold over and encapsulate the fluid in these vacuoles that you see in this sort of X-ray view here. Now, there was one problem with this approach, in that it was physically took too long to step that beam to capture data at that rate. So what we did is we used a diffractive optical element to create an array of 7 parallel Bessel beams to speed it up 7-fold. That was effective, but what was shocking was how much less toxic it was to run with 7 beams instead of 1. And what I've discovered in doing 7 years now of live cell imaging is, while the total dose of light you throw at the specimen is important, a far more important metric is the instantaneous power delivered to the cell. So seen in this light, the confocal microscope, which is really the gold standard of live cell imaging, may be the stupidest possible way to do live cell imaging, because not only do you have these cones of light above and below the focus that's causing unnecessary bleaching and toxicity, at the focus itself you have this actinic spot of light that's going, and it's leaving death and destruction in its wake. And so the moral of the story is, a line is better than a point and a plane is better than a line. So what that means is, why stop at 7 beams? Well, the reason we stopped at 7 is we were worried about what would happen to these Bessel beams when the side lobes interfered. So I started to model what would happen as the beams came closer together. And what you find is, you go through these resonances of constructive and destructive interference, but you find certain magic patterns where 3 wonderful things happen. First, you get near perfect destructive interference of all of the side lobes, so that nasty side lobe problem goes away. In the plane, you have 100% modulation of the excitation, which is ideal for high SNR sim imaging. And third, you spread all of the light across the plane to minimize the peak power. So basically, it's a triple win. I'm an engineer at heart. Triple wins are as common as unicorns. When you find one, you embrace it and you take it home. And so this is what we did. And you can either use this structured light sheet in a structured illumination mode, or you can dither it back and forth and take 1 image per plane, which is faster but lower resolution, and then really move quickly. So this is what we call the lattice light sheet microscope. Now, in some ways, I felt like an idiot after realizing about these magic patterns, because it turned out that these magic patterns are exactly the periods that I predicted 10 years earlier in that optical lattice theory that I generated and then abandoned in order to do Palm. But once I finally realized that connection, I could take all of that stuff out of the wastebasket and actually apply it and figure out what would be the most ideal 2D optical lattices to apply to the light sheet microscopy. And that's why we call it the lattice light sheet microscope. So this is some examples from that microscope. So basically there's a 2D lattice confined to a plane, then swept to create a sheet. And then that excites that orange fluorescence you see, and then we drive the cell through it. Like a Xerox scanner, you get your 3D volume. This is an example. Most of what we know about cell motility is looking at cells on cover slips, but it's pretty damn poor model for cancer metastasis. But here you're looking at a cell actually migrating through a collagen mesh with Dyke-Mullins group. And so that's a much more realistic model. Here you're looking at a model organism called Tetraimina. It's a pond protozoan. In this case, he's trapped in a pocket of transparent agarose and is trying to twerk his way out of there. But, you know, again, you're looking 3 volumes per second for over 1,000 time points. There is no other microscope on Earth that can do 3D imaging of live cells for anywhere near this fast or anywhere near this long. Here you're looking at Dictystelia, which is a light-sensitive slime mold, amoeboid. And if you watch this movie go, you just saw that lightning bolt. So when we saw that, we asked our collaborators, what the hell was that? And they said, we don't know. And so, you know, the nice thing about this microscope, look, it's fine to win the Nobel Prize for Palm. I know I've been very derogatory of Palm and super resolution general in this talk. Trust me, I love Palm, and it has a lot of application. I'm just trying to act as a counterweight to everything else that you hear. But there is a lot of plus. But still, although I won the Nobel Prize for that, I'm morally convinced that this is the microscope that's going to have the most impact out of my career. Because of over 50 different groups who've come to use it, everyone goes away with huge smiles on their face. And in a week, they go away with 10 terabytes. And then the smiles vanish because they have no idea about what the hell to do with 10 terabytes of data. And so, again, we are drowning in data. And anytime our collaborators publish a paper or you make a movie like this, 99.999% of the data is hitting the cutting room floor. And there's so much to be mined and so much to be learned. And we need big data experts like from LBL. We need physicists who know how to analyze this type of data. It's a major problem and it could use a lot of help. But I have never felt more like Galileo than I have with this microscope, because every new sample that we pointed at is an adventure and a really great time with our collaborators. So if you like these movies, I suggest you check out our Vimeo album, which has like 30 different examples of seeing cells doing their thing. So as it turned out, you know, although I had moved away from single molecule and super resolution, it just became too damned attractive to go back, because it turned out that lattice light sheet is the ideal tool for single molecule imaging. Because one of the things that's swept under the rug in the single molecule field is that you're doing wide field imaging of these molecules usually. And if the sample is more than a few microns thick, the out of focus molecules create so much background you have no chance of seeing the ones in focus. But with the lattice light sheet, you can just park that lattice plane anywhere you want, and then you get almost turf quality signal to noise to see the single molecules, because the lattice light sheet is actually thinner than the depth of focus of even a high NA detection objective. So you're only illuminating in focus molecules. And so it's become a really great tool for doing, in this case with our transcription imaging consortium, to look at the binding kinetics of transcription factors to DNA. Based on the residency time, you can determine what's specific or non-specific and find that there are specific hotspots of binding of certain transcription factors to the DNA. In a later paper, James Liu, who was part of the TIC and now has his own lab at Janelia, was able to show that these enhancer clusters, as he calls it, are actually spatially segregated from heterochromatin in the nucleus. And now in MCB, they have a new lattice scope running. We've executed about 60 different research licenses with various groups who are building lattice scopes. We just had a workshop at Geneva where 35 of those groups came. We tore apart a microscope and put it back together again so they can see how it's done. So this stuff is starting to take off pretty quickly at this point. But it also led me back to doing single molecule localization microscopy, because again, remember I said the main challenge of super resolution is getting a high enough density of labeling to decorate things and get enough spatial frequencies in your sample. And the problem with standard super resolution is you use genetically encoded markers or dyes and you put them in at time equals 0, you fix your cell, and now you have a finite budget of molecules to work with. Well, in the same year that we published our Palm paper, Robin Hochstrasser's group at Penn published a related idea which doesn't use photoactivation, but is based on the fact that you put in your media around the cell fluorescent molecules. And normally they're whizzing around in a Brownian motion so fast you don't see them. But when they bind and stick to their targets, then they're a little star, and then you can localize that. The advantage of paint is that there's an infinite army of molecules in that media, and if you wait long enough, you're going to get a lot of localization events. So a typical localization microscope image by photoactivation might have 500,000 molecules. This is 2 orders of magnitude higher than that. Now, the disadvantage of paint is that your whole media is glowing, and so the signal noise is crummy. But if you apply lattice light sheet to it, then the signal noise is great, and then you can get to very high localization densities. And the other advantage is now you're not restricted to looking at very thin samples by single molecule techniques. So here you're looking at a dividing cell in anaphase where you can see the 2 daughter cells forming. You can see one paint label at the plasma membrane, and another looks at all the intracellular membranes on the inside. You can even take that up to something as large as a zebrafish. In this case, we're looking at a neuromassed organ which is along the lateral line of the zebrafish, and as we cut away, you'll see all of the cells that make up that neuromassed organ. So now we can really take localization microscopy to where it should be and where it should have been 10 years ago. So there's one final challenge that we face, and that's, in my opinion, speaking as a non-biologist who looks at biology from afar, I'm worried that we have never seen the cell the way the cell is. I'm not sure we've ever looked at a physiological cell because of several things. First off, we often put on our GFP inside of that cell. The GFP acts as a little bowling ball, and usually the expression of the protein is uncontrolled. So now you've got this oversupply of one protein. It's changing the whole homeostatic balance of the cell. Now you throw that in your confocal microscope, which, like I said, is just blazing away and changing the physiology from the light. And then furthermore, you're looking at some cell that's on a cover slip, and it's damn sure they didn't evolve there, okay? So you basically need to combine 3 things. We need to take CRISPR-Cas9 genome editing technology so we can control the expression of our fluorescent proteins to match endogenous levels. Now, those levels are generally lower than they are in normal experiments people are used to, so you need a non-invasive, highly sensitive imaging tool that's fast enough to then be able to look at that. That's where the lattice light sheet comes in. But there's a third part of the puzzle, is we have to move away from the cover slip and study those cells and the organisms they evolved in so we can see all the cell-cell signaling that's going on and everything else. The problem with that is that biology, by definition, has to be heterogeneous. And therefore, there's refractive index differences that scramble the light sheet that's going in and scramble the light sheet from the fluorescence that's coming out, the same way that water on the windshield scrambles what you can see in front of you. And so we have to apply the tricks of adaptive optics, which were first developed by the astronomical and military communities around 50 years ago. So what they do in astronomy is they shine a laser into the atmosphere to excite some sodium atoms to create a bright artificial point called a guide star next to the astronomical feature they care about. Both of those things follow the same path through the atmosphere into the telescope. Use a beam splitter to pick off the guide star light, put it in something called a Shack-Hartman wavefront sensor to determine the distortion of the wavefront, close the loop in a computer, change the shape of a deformable mirror to exactly balance it, get your flat wavefront, and recover your diffracted limited performance. And so About once a year, I give a talk on the historical connections between astronomy and microscopy. The theme of that talk ends up being that microscopists are the retarded stepchildren of astronomers, and they figure everything out 50 years before we do. And I think adaptive optics is going to be yet another example of that. So while in astronomy you put that thing in the stratosphere, a group in Spain a couple years ago had a good idea of using a 2-photon microscope, which just excites fluorescence locally instead of in that cone, to create a spot that way. So we added some tricks that came from the ophthalmology AO community about doing D-scan to get rid of some additional speckle modal structure that you have in this case and to reduce the requirements for targeting. And that turned out to be quite effective. So here we're looking at a zebrafish that's 3 days post-fertilization, looking in the spinal cord region at a pan-membrane label of neurons, and you can see before the AO, because all of the light rays are not coming to perfect focus, but going kind of willy-nilly, that's a really bad squishy focus of low intensity that gives you this. Now, once you correct that and get all of the rays in focus at the same point and with the same phase, then you get a high signal and you get high resolution. You guys probably heard my wife, Naji, talk about this in the colloquium a month or so ago. So she's the world's expert in this, and she has a whole suite of tools for how to do this even in scattering media where you can't see a guide star. In my case, because I'm interested in applications just a light sheet, and the light sheet would get screwed up by all the scattering anyway, I can do these more simple sort of direct things for the limited class of problems where they can be applied. In my case, I'd be happy if I could spend the rest of my life studying the zebrafish, because I love that as a model organism and there's a lot to learn. So here's the fish now, looking in the brain of the fish, again about 3 days post-fertilization, looking at a sparse subset of neurons. Now, another thing that is common to astronomical and microscopy AO is that the correction you have in one area is uncorrelated after a little distance to the correction required in another area. So you have to do many, many corrections. Over this volume, we had to do 20,000 adaptive optic corrections. But because the speed of the microscope imaging is much slower than the correction, it doesn't slow us down. Now we're turning the AO off in the midbrain region fish. That's what you would see with a state-of-the-art 2-photon microscope. That's what you see when you turn the AO on. It's not super resolution, it's just getting back to the diffraction limit. And it's meant to show biologists who are doing developmental biology and neurobiology that if they believe they were at the diffraction limit in the imaging they were doing, we're trying to tell them, it's not anywhere near it. This is an example where we can do cell biology deep inside of the fish, where these are the mitochondria, the power sources of the cell, and it's just a fuzz without the adaptive optics. But once we turn on the adaptive optics, and since we know the point spread function, we can do a deconvolution, then you see those mitochondria as well as if this were a cell on the cover slip. And this is our goal. Again, to marry CRISPR-Cas9, lattice light sheet, adaptive optics, to finally try to see the cell on its own terms and make it a powerful tool for both cell and developmental biology. So in order to do that marrying, it's a pretty complicated beast. So this is the lattice light sheet here. This is the detection arm adaptive optics to correct the light coming out. This is the excitation arm to correct the light sheet going in. And this is the path of the lattice. So it's really 3 microscopes being fused into one. But this is some of the initial results looking at a membrane-labeled zebrafish. This is with the adaptive optics off, and you can see as you go deeper and deeper, you can see the loss of resolution. But now in a second, we're going to first turn on the detection correction. And no. And then we're going to turn on the excitation correction. And then we're going to do our deconvolution. And now we can actually see all these extracellular spaces, really small extracellular spaces between the cells, even 100 microns plus deep inside of the thing. Now it also means that all those single molecule tricks to study transcription and so forth also come into play. So there's a lot of things we can do with this. The problem, so like when I showed you that brain just a minute ago where we looked at the large volume of neurons, the downside was the imaging speed is slow because it's point scanning. And remember, I'm the guy who hates point scanning in microscopy because it's slow and death to things. And that's why you need the lattice. So whereas that large volume required 18 hours to get, This is a similar volume that we're getting in 7.5 minutes now because it's using the lattice in order to get the data. And then instead of looking at one time point, we can do dynamics here for 75 time points and watch the cells divide as the embryo evolves. So this is really kind of the state of the art of where we are in the group, and we're going to start really applying this method to really take the lattice to the multicellular. So very quickly, 2 projects in the pipe right now. Where are we going in the future? One is that the reason you get resolution in a diffraction-limited microscope is from the collision of wave vectors. The more wave vectors that can collide head-on, the higher the resolution you can get, either in diffraction-limited microscopes or in SIM. So you need to come from more directions. This is the crazy microscope we're building now, which has 2 opposed detection objectives to get the highest resolution on detection axially, with 3 lattice light sheet microscopes in the plane to be able to interfere pairs of those to get very high numerical aperture excitation to take our standard lattice resolution from this to this. And so that's actually, all the parts are in, and while I'm on the road having no fun, Wes is having all the fun back in the lab of putting this thing together and seeing if we can get to that point. But this microscope will be amazing if it works in terms of what you'll see. It'll put everything we've done to lattice so far to shame. And the last and crazy project that I'm excited about is everything I've discussed that we're doing in the group now, I'm pretty damn confident is going to work. But I'm at Genelia Farm, damn it, and if there's anybody who should be able to take risks, it's me. I got a goddamn Nobel Prize, and I've got all the money Howard Hughes could ever throw at me. So, you know, why can't I do something stupid, right? So I'm teaming up with Harold again, who's the best low-temperature physicist I have ever known. And so we're saying, well, let's go back to the beginning where W.E. was when he was looking at the spectral signature of signal molecules. I mean, then he was looking in p-terphenyl or other crystals, but, you know, damn it, with cells you have to look in ice. Vitreously frozen cells so we can preserve the ultrastructure with high-pressure freeze. And we're doing what we call a fishing expedition. So the advantages are, again, you preserve ultrastructure versus chemical fixation. You can freeze out a lot of things that would cause fluorophores to bleach. And the line widths can narrow in an ensemble a fair amount, but there's still a lot of inhomogeneous broadening, or in singles, right down to the 0 phonon limit. And so, for me, there's 2 holy grails of microscopy still. The first is a normal cell has up to 10,000 different types of proteins in it. Yet normally with fluorescence, we study them 2 or 3 at a time because the bandwidth of the fluorescence emission is so broad, that's the most you can do. But if you can get very narrow line widths, potentially we could study dozens or hundreds of proteins all involved in, say, one signaling pathway at the same time and unravel the whole mystery of it in one fell swoop. Okay, so that would be one goal. The other goal is I have a love-hate relationship with fluorescence because it's an interloper. It's this bowling ball that you're sticking on, and it's imperfect, and it's a proxy for the thing you care about, which is the target protein it's attached to. So there's been lots of work over the years in trying to do label-free imaging. A lot of it based on CARS or stimulated Raman spectroscopy. But the problem is these things are largely sensitive to lipids, and it's proteins you'd like to care about. We're interested in this fishing expedition to see that if we explore at low temperatures, whether we can find other spectral signatures where we can bang harder because everything's a rock at 4 Kelvin, and see if we can actually then do some label-free imaging. So really, it's just something, a playground for Harold and I to play with. It's the only lab in Genelia that looks like the qubit lab I saw earlier today. We've got helium and everything else, but it's fun. Go back in the beginning, think like physicists a little bit, and we'll see what comes out of that. And so that's the experiment that I'll finish this. So the final thing I want to say is one thing that's very important to me, and this is something that I think LBL could also help with. Is none of this papers mean it only matters. Matters is biologists answer a question that could not be previously addressed by any other technology. To get that, they have to be in the hands of biology. And it's a long road. Something physicists build who turn hands into biologists. So we're taking a three-pronged approach to that agenda. The first is that we copiously document how to construct these things. We give out code and all the rest. So if you sign a research license, we give you everything you need to build your own lattice. But you have the technical chops to do that. Even before that or after that, if you're a biologist, we've created with the Gordon Moore Foundation an advanced imaging center in Amelia, where only for outside users, where they can come in and use a copy of our lattice scope, use Harold's exquisitely sensitive 3D IPOM microscope, use our fast linear and nonlinear structured illumination microscope, etc. And this has been wildly successful. These microscopes are incredibly popular. They're oversubscribed. At some point, we need to create something like a Genelia West. I think Berkeley wouldn't be a bad place, and the LBL would be a bad place. The other thing that's going to happen with these things, though, is you need infrastructure around it. It isn't just the microscopes, it's all the sample prep, and then on the outside end, it's about all of the analysis and handling of big data. On the big data, that's where we're still really weak, and that's where we need a lot of help. And then the final step is you create a market for these microscopes through the papers that are being published by the people who come out of here to get to the point where the companies are willing to make the development investment necessary to make that turnkey microscope where finally the biologists can have them all in their hands. And that's what we're aiming for. And so with that, I'd like to close, and there's so many people to thank. But again, we've had over 70 different biological collaborators come to our group, and they're really what makes it go. You know, we learn so much from them and learn what we have to improve. I also have to thank my postdocs. Everything you've seen in this talk is the product of 5 guys, and on average, more about 3 guys over the course of my career. So these guys drink the Kool-Aid. They understand the importance of what they're doing, and they work their butts off, oftentimes 18 hours a day. They're very much like Harold and I were back in the day. And I really believe that there's nothing like hard work. Hard work beats brains any day. And these guys have both the brains and the hard work, so that's an even better combo. But I'm really indebted to them and many, many other great collaborators I have at Genelia. Thank you for your time. Happy to take any questions.
Yeah, I think we have time for just a few questions.
Don't tell me I'm intimidating them all. Come on. Somebody's got to uphold Berkeley honor here, yes.
What are the prospects of using these physics to improve the resolution of functional magnetic resonance imaging?
I think there is possibilities there. I mean, I've always been, very jealous of maybe not the functional MRI, but just regular MRI, right? In terms of, and I love the concept that, you take a gradient and spectroscopy and could get spatial information out of that. In fact, in that same paper I published in '95, that was the idea palm, in that same paper I pitched, since I had been doing near-field microscopy, to basically put an electric field on the near-field probe of some molecules near there and split them by Stark effect, and then use an MRI type principle net gradient to localize and position them that way. And people have done that a little bit now with NV centers and like that. But so maybe, I don't know about what we can do to improve functional MRI because I'm no expert in that, but I think that principle of gradient imaging is a powerful one. And whether it's done with light or acoustics even, or other things, there was a paper recently in Nature, this is a little off topic from your question, about using the palm principle to do ultrasound imaging, because they can cavitate little bubbles at different frequencies that resonate, and then they can localize them and go much past the normal limits of ultrasound and resolution of ultrasound. So I think a lot of these ideas that we have here are applicable to other modalities if we think hard about it. Yeah, Austin.
Are you constrained by you use a lot of store-bought, off-the-shelf objectives for your
Yes.
microscope?
Yes.
Do you feel constrained by that because you're using the non-conventional ways? Have you thought about designing it over your own?
Well, yeah, so the lattice light sheet does have a custom objective. So In that case, you know, we wanted to optimize the numerical aperture of detection within the limits of working distance we wanted. So that got us a 1.1 NA objective. So that has a certain solid angle to it. We wanted to look at cells or embryos on a cover slip, so there was some residual solid angle. There was no commercial instrument that would have the working distance and the dimensions necessary to fill that space. So we had a custom objective made to fill the remaining pie of solid angle. And the space is so tight, it's an 8-element lens. The last 3 elements actually have no metal around them at all. It's only the optical cement that holds them, because otherwise the metal would take up too much space. So we have done a little bit of that. There's other, within Janelia, optimized instruments like scan lenses on microscopes, and Carl Svoboda has recently made a very large field of view 2-photon microscope for population and structural imaging that's all custom made. But for us, it's only with the lattice scope that we've had to dabble in it, but we're happy to dabble in it when it becomes necessary.
One more question. So in your adaptive optics application, how do you create the equivalent of aperture star?
So for us, it's a 2-photon microscope. So in 2-photon microscopy, by using a femtosecond laser, the excitation is only created at the focus. So therefore, you have that sort of localized spot you need. Now, the problem is that if you actually do a correction based on parking it at some point, the one way that astronomical AO differs from microscopy AO is that the Zernike modes involved in the correction are much greater in microscopy. It's a much gnarlier environment than the atmosphere. So gnarly that in a standard Shack-Hartman sensor, you don't get little spots in the individual segments, you get speckles, okay? If, however, you scan your guide star over a region, you average those speckles out. And then the Shack-Hartman can give you an accurate representation of the lower order aberrations over that region. It turns out that actually ends up to be a more accurate correction, even at the point if you just park the spot at one spot. So that's the trick that we added that makes it very robust.